In this video, I will be discussing OSV mechanics. I am going to focus on the forces that are being applied to the OSV in motion and how to draw a free body diagram for an OSV that is traveling on the sand as well as off the sand. I will now discuss the forces that act on the OSV and its wheels when traveling on a hard surface. So this is just obviously a very basic picture that we're going to come back to. So there's obviously very many forces that will be acting on this OSV when it is in motion. And first we're going to focus on the forces that are acting on the wheels. So the first wheel that I want to focus on is a drive wheel. And a drive wheel basically just means that it is attached to a motor. So something is going to make it move forward, which is obviously necessary in order to complete the OSV mission. So the first force that many of you might think of is the weight. So the weight is just a downward force acting at the center of the wheel, representing the weight of the wheel, obviously. Then there's also a normal force at the contact surface. So this pushes up on the wheel here. The weight is represented by W, and the normal force will be represented by F of N. So the weight acts down, the normal force counteracts that, acts upward. Important thing to consider in a free body diagram before I forget is to identify your axes. So that was really bad, obviously. This is X, this is Y. And the sum of the forces is going to be equal to 0, as well as the sum of the moments. So these are the first two forces that we're going to focus on. And then, since this center point is usually the connection point between the wheel and the rest of the OSV, there's two reaction forces that we're going to assume to be in the positive direction that basically just connect the wheel to the rest of the OSV, which is obviously important. Alright, now once we have those, since this is a drive wheel free body diagram, the main difference between the drive wheel and the non-drive wheel, which a non-drive wheel is obviously just not connected to the motor, but since this one is, it's going to have a torque. And this torque is going to act around the center of gravity, and it's going to be represented by tau. And so basically, this is what spins the wheel. As the motor spins, it spins the wheel, creates this net torque. But if you look at this now, the net moments are not going to be equal to 0 because this torque is counteracting all of this movement. So now, what we have to consider is a force of traction. And this force of traction is basically just countering the torque, and it is what is actually pushing this wheel forward and causing the OSV to move forward. And is an important equation involved in this is that the torque is going to be equal to this tractive force times the position vector r, which in this case just looks like it is the radius, but normally it's just a position vector from the point where the force is being applied, so where F of t is being applied, to the point where the torque is being applied. So this, let me get a different color. So this distance is going to be r. So basically this concludes all of the forces that are going to be involved for an OSV. And before I forget to mention, this is an OSV on a hard surface. So when the OSV travels on sand, there's another force to be taken into consideration, which we're going to get to later. The next thing I'm going to discuss is the free body diagram of a non-drive wheel, which is one with no motor. And it's going to be based on the forces on a hard surface. Downward force of weight, it's going to have the same reaction forces, R of Y and R of X. It's going to have a normal force. The only thing that it's not going to have is not going to have the torque, and it is not going to have the force of traction. Now I want to go back to the whole vehicle, so the whole OSV. And so what we're going to see in this free body diagram that I'm about to draw is that a lot of these forces that are acting on the wheels are not going to be incorporated in this total free body diagram. So I'm going to draw my axes. And the first thing I'm going to start with is the weight. So this is just going to act at the center of gravity, center of mass, W, which is obviously, it's changed because this is the whole system now. And then the only other two forces that we're going to consider on the wheels are this normal force. So those are going to be on both of the wheels. Then there's going to be this force of traction. So this is what's ultimately moving it forward. Now the one difference between this is there's going to be a force resisting this. So this So F resist is going to be countering the force of traction, making it so the sum of the forces is equal to 0. I'm now going to discuss the difference between the forces that are being applied to the OSV when it travels on the sand. So the first thing I want to focus on are the wheels. So this is the drive wheel, which is the two wheels in the back of the OSV that in this particular example. And it's still going to have the reaction forces that connect the wheel to the actual OSV. It's still going to have the force of the weight, and it is still going to have the torque, which is caused by the motor. The difference between the wheel on the sand is that the normal force, represented by F of N, the normal force is going to be on the bottom front of the wheel instead. And there's also going to be a force applied to the opposite direction, FRR, and this is going to be the rolling resistance. So these two forces are both the forces caused by the sand. And then we're still going to have this force of traction, which is still going to be located on the center bottom of the wheel. In the case of the non-drive wheel, it's fairly similar to the drive wheel. Just doesn't have the torque and the attractive force. So I just identified the line that goes through the center of mass to make sure that the sum of the force are equal to 0 and the sum of the moments are equal to 0. So going back to this line that goes through the center, there's going to be two forces. The one in the y direction is just going to be the normal force, which is going to be on the bottom right again. And then the force that's pointing towards the left is going to be the rolling resistance. And both of these are going to be the x and y components of the force of the sand. And it's important that this force goes through this diagonal line so that the moments are equal to 0, because by pointing in this direction it will have no moment, and therefore equilibrium will be maintained. So now that we've identified both of the wheels, I'm going to talk about the OSV as a whole and how these forces are different. So there's still going to be the tractive force on this reel with the motor. Just identify my axes. And in this case, as shown on the wheels, this normal force and the rolling resistance are both going to be on the bottom right of the wheel. This is the case on both. The non-drive wheel that doesn't have a motor, the only difference is that it doesn't have the tractive force, obviously because it has no torque, and the weight still goes down in the center. Now it's important to note that for this oversand vehicle, the ratio between the tractive force and the rolling resistance is a 2-to-1 ratio. So F of T is going to be equal to 2FRR. And this can be found by doing your, you can set the sum of the forces about X equals to 0. And it is found that there are, so the only forces involved in the X direction is going to be these two, the two rolling resistance, which would be going in the negative direction, and this force, which is going in the positive direction, which is the force of traction. The OSV previously discussed was a two-wheel drive, meaning that the tractive force is equal to twice the amount of rolling resistance. If the OSV were a four-wheel drive, meaning there would be 4 motors and 4 wheels instead of only 2 motors, then the tractive force would be equal to the rolling resistance.